Lecture 1. The pH scale. The pH scale describes how acidic or basic a solution is. At 25 degrees Celsius, a pH below 7 is acidic, a pH of 7 is neutral, and a pH above 7 is basic. The scale is logarithmic. A difference of 1 pH unit represents a 10-fold difference in hydronium ion concentration. For example, a solution with a pH of 3 has 10 times more hydronium ions than a solution with a pH of 4. A lower pH means a higher hydronium concentration, while a higher pH means a lower hydronium concentration. Lecture 2. pH, pOH, and concentration. pH measures hydronium ion concentration, while pOH measures hydroxide ion concentration. To calculate pH, take the negative logarithm of the hydronium concentration. To calculate pOH, use the negative logarithm of the hydroxide concentration. We can reverse the calculation by raising 10 to the negative pH or pOH. At 25 degrees Celsius, pH plus pOH equals 14. For example, if the pH is 3, the pOH is 11. Remember that a smaller pH means more hydronium ions, while a smaller pOH means more hydroxide ions. Lecture 3. Autoionization of water. Water can react with itself to produce hydronium and hydroxide ions. One water molecule transfers a proton to another water molecule. This process is called the autoionization of water. At equilibrium, the hydronium concentration multiplied by the hydroxide concentration equals Kw. At 25 degrees Celsius, Kw is 1 times 10 to the negative 14. In pure water, hydronium and hydroxide concentrations are equal. Each concentration is 1 times 10 to the negative 7 molar. This gives a pH of 7 and a pOH of 7, making pure water neutral at this temperature. Lecture 4. Temperature and neutrality. A neutral solution does not always have a pH of exactly 7. Neutral means that the hydronium and hydroxide ion concentrations are equal. The value of Kw changes with temperature. As temperature increases, water generally produces more hydronium and hydroxide ions. The neutral pH can therefore become lower than 7. The water is still neutral because both ion concentrations increase equally. At lower temperatures, the neutral pH may be greater than 7. When deciding whether a solution is neutral, compare the hydronium and hydroxide concentrations instead of looking only at the pH value. Lecture 5. Strong acid dissociation. A strong acid ionizes almost completely in water. Hydrochloric acid, for example, transfers a proton to water and produces hydronium and chloride ions. Because the ionization is essentially complete, very little intact hydrochloric acid remains. For a monoprotic strong acid, 1 mole of acid produces approximately 1 mole of hydronium ions. Remember that acid strength and concentration are different. Strength describes how completely the acid ionizes. Concentration describes how much acid is present. A dilute strong acid can sometimes contain fewer hydronium ions than a concentrated weak acid. Lecture 6. Calculating the pH of a strong acid. Consider 0.016 molar hydrochloric acid. Hydrochloric acid is strong and monoprotic, so it ionizes completely and produces the same concentration of hydronium ions. The hydronium concentration is therefore 0.016 molar. Taking the negative logarithm gives a pH of approximately 1.80. Always use the balanced equation before calculating pH. First, determine how many hydronium ions are produced. Then calculate the correct concentration and finally take the negative logarithm. The logarithm should be the final step of the calculation. Lecture 7. Strong bases and pH. Strong bases dissociate completely and release hydroxide ions. Calcium hydroxide produces 2 hydroxide ions for every formula unit that dissolves. If calcium hydroxide has a concentration of 0.01 molar, the hydroxide concentration is 0.02 molar. Taking the negative logarithm gives a pOH of approximately 1.70. At 25 degrees Celsius, subtract the pOH from 14. The pH is approximately 12.30. Always check the balanced equation because the base concentration may not be equal to the hydroxide ion concentration. Lecture 8. Strong acids versus weak acids. A strong acid ionizes almost completely, so the solution contains mostly hydronium ions and conjugate base ions. A weak acid ionizes only partially and establishes an equilibrium. Most weak acid molecules remain intact, while only a small portion produces hydronium ions. Strong and weak describe the extent of ionization, not concentration. A concentrated weak acid may contain more total acid than a dilute strong acid. Therefore, we need both acid strength and concentration to predict pH. Weak acids also require an equilibrium calculation because their ionization is incomplete. Lecture 9. Weak acid equilibrium. A weak acid can be represented as HA. It reacts with water to produce hydronium ions and its conjugate base, A-. Because the acid ionizes only partially, the reaction is reversible. The acid dissociation constant, called Ka, describes the position of this equilibrium. A larger Ka means that more acid ionizes and more hydronium ions are produced. This represents a stronger acid. A smaller Ka means that most of the acid remains intact. To calculate the pH, we must combine the Ka value with the initial acid concentration. Lecture 10. Weak acid ice table. An ice table organizes initial, change, and equilibrium concentrations. Suppose the initial weak acid concentration is C. The initial product concentrations are treated as approximately 0. If X molar of the acid ionizes, the acid concentration decreases by X. The hydronium and conjugate base concentrations each increase by X. At equilibrium, the concentrations are C minus X, X, and X. Substituting them into the Ka expression gives X squared divided by C minus X. After solving the equation, X represents the hydronium concentration. Taking its negative logarithm gives the pH. Lecture 11. Weak base equilibrium. A weak base accepts a proton from water but does not react completely. A general weak base, B, reacts with water to form its conjugate acid, BH+, and hydroxide ions. The reaction is reversible and establishes an equilibrium. The base dissociation constant is called Kb. A larger Kb means that the base reacts more and produces more hydroxide ions. This represents a stronger base. After calculating the equilibrium hydroxide concentration, take its negative logarithm to find pOH. At 25 degrees Celsius, subtract the pOH from 14 to obtain the pH. Lecture 12. Weak base ice table. The ice table for a weak base follows the same pattern as the weak acid table. Begin with an initial base concentration of C and approximately 0 product concentrations. If X molar reacts, the base concentration decreases by X. The conjugate acid and hydroxide concentrations each increase by X. At equilibrium, the concentrations are C minus X, X, and X. Substitute these values into the Kb expression and solve for X. Here, X represents the hydroxide ion concentration. Use it to calculate pOH and then convert pOH into pH. Lecture 13. Percent ionization. Percent ionization tells us what percentage of a weak acid ionizes. Divide the equilibrium hydronium concentration by the initial acid concentration and multiply by 100%. For example, suppose a 0.100 molar acid produces 0.0010 molar hydronium ions. The percent ionization is 1.0%. This means that only about 1% of the acid molecules ionized. Percent ionization usually increases when a weak acid is diluted, although the total hydronium concentration may still decrease. Lecture 14. Conjugate acid and base strength. Every acid forms a conjugate base after donating a proton. Every base forms a conjugate acid after accepting a proton. The strengths of a conjugate pair are inversely related. A strong acid produces an extremely weak conjugate base. A weaker acid produces a conjugate base with a greater ability to accept a proton. For a conjugate pair, Ka multiplied by Kb equals Kw. If Ka is known, divide Kw by Ka to find Kb. A large Ka corresponds to a small Kb. Lecture 15. What determines acid strength? Acid strength depends on how easily the acid releases a proton. One important factor is the strength of the bond holding the hydrogen. A weaker bond is generally easier to break. Bond polarity can also affect acidity. If the bonded atom pulls electron density away from hydrogen, the hydrogen becomes easier to remove. The stability of the conjugate base is equally important. If the negative charge left behind is stable, proton loss becomes more favorable. Acid strength is therefore influenced by bond strength, bond polarity, and conjugate base stability. Lecture 16. Stability of the conjugate base. A more stable conjugate base corresponds to a stronger original acid. Several factors can stabilize the negative charge. Resonance spreads the charge across multiple atoms. Electronegativity stabilizes charge on atoms that attract electrons strongly. Larger atoms can spread negative charge over a greater area. Nearby electronegative atoms can also pull electron density through bonds. This is called the inductive effect. By examining resonance, electronegativity, atomic size, and induction, we can compare acid strengths without memorizing every Ka value. Lecture 17. Acid-base stoichiometry. Before using an equilibrium calculation, check whether a neutralization reaction occurs. Hydronium and hydroxide ions react in a 1:1 mole ratio to form water. First, calculate the moles of each reactant by multiplying molarity by volume in liters. Next, use the balanced equation to determine the limiting reactant and calculate how many moles remain. If a concentration is needed, divide the remaining moles by the total solution volume. In acid-base mixtures, complete the stoichiometric reaction first. Equilibrium calculations should only be performed after the neutralization step. Lecture 18. Weak acid and strong base reactions. When a weak acid reacts with a strong base, hydroxide ions convert the weak acid into its conjugate base. The reaction proceeds almost completely. Before the equivalence point, both the weak acid and conjugate base are present. This mixture acts as a buffer. At the equivalence point, nearly all the weak acid has been converted into its conjugate base. The conjugate base reacts with water, making the solution basic. After the equivalence point, excess hydroxide ions control the pH. The correct calculation depends on which stage of the reaction has been reached. Lecture 19. Reading a titration curve. A titration curve shows how pH changes as titrant is added. Begin by identifying the initial pH. Next, locate the region where the pH changes gradually. In a weak acid titration, this is the buffer region. The half equivalence point is found halfway to the equivalence volume. At this point, the pH equals pKa. The equivalence point is located near the center of the steepest section of the curve. Beyond this point, excess titrant controls the pH. Each section of the curve represents a different chemical situation and requires a different calculation. Lecture 20. Strong acid and strong base titration. In a strong acid and strong base titration, both substances dissociate completely. Before the equivalence point, excess strong acid determines the pH. At the equivalence point, equal moles of acid and base have reacted. The remaining salt does not significantly react with water. At 25 degrees Celsius, the equivalence point pH is 7. After the equivalence point, excess strong base determines the pH. The curve has a sharp vertical change near equivalence. Because this pH change covers a wide range, several different indicators may be suitable. Lecture 21. Weak acid and strong base titration. A weak acid and strong base titration begins at a higher pH than a comparable strong acid titration. As the base is added, some weak acid is converted into its conjugate base. This creates a buffer. At the half equivalence point, the weak acid and conjugate base are present in equal amounts. Therefore, the pH equals pKa. At equivalence, the conjugate base reacts with water and produces hydroxide ions. The equivalence point pH is therefore greater than 7. After equivalence, excess strong base controls the pH. Lecture 22. Weak base and strong acid titration. In a weak base and strong acid titration, the pH decreases as strong acid is added. Before equivalence, the weak base and its conjugate acid form a buffer. At the half equivalence point, equal amounts of the weak base and conjugate acid are present. At this point, POH equals pKb. At equivalence, the solution contains mainly the conjugate acid. This conjugate acid reacts with water and produces hydronium ions. Therefore, the equivalence point pH is below 7. After equivalence, excess strong acid controls the pH. Lecture 23. Weak acid and weak base titration. A weak acid and weak base titration usually does not have a large, sharp pH change near the equivalence point. Both reactants are weak, and the ions in the resulting salt can react with water. The equivalence point pH depends on the relative values of Ka and Kb. If the acid is stronger than the base, the solution tends to be acidic. If the base is stronger, the solution tends to be basic. Because the pH change is gradual, indicators may not give a clear endpoint. A pH meter is generally more reliable for this type of titration. Lecture 24. The half equivalence point. The half equivalence point occurs when exactly half of the original weak acid has been neutralized. At this moment, equal amounts of the weak acid and its conjugate base are present. In the Henderson-Hasselbalch equation, the conjugate base to acid ratio is 1. The logarithm of 1 is 0, so the pH equals pKa. The amount of titrant added is also half the equivalence point volume. This relationship provides a convenient way to determine the pKa and Ka of an unknown weak acid by examining its titration curve. Lecture 25. Polyprotic acid titration. A polyprotic acid can donate more than one proton. A diprotic acid donates 2 protons in separate steps. The first proton is removed to form an intermediate species, and the second proton is removed afterward. Each ionization step has its own Ka value. The first Ka is normally larger because removing the first proton is easier than removing a proton from an already negative ion. If the 2 Ka values are sufficiently different, the titration curve shows 2 buffer regions and 2 equivalence points. Each equivalence point represents the removal of 1 proton from the acid. Lecture 26. How acid-base indicators work. An acid-base indicator is usually a weak acid whose acid and base forms have different colors. The acid form can release a proton and become its conjugate base form. When acid is added, the equilibrium shifts toward the acid form and its color becomes dominant. When base is added, the equilibrium shifts toward the conjugate base form, producing a different color. The color does not change at one exact pH. Instead, it changes gradually across a transition range centered near the indicators pKa. Different indicators have different transition ranges and colors. Lecture 27. Choosing an indicator. A suitable indicator should change color during the steep section of the titration curve. Its transition range should include or be very close to the equivalence point pH. The indicator does not need to change at exactly the equivalence point. However, its transition should occur while the pH is changing rapidly. This keeps the visible endpoint close to the true equivalence point. Strong acid and strong base titrations allow several indicator choices because their pH change is very large. Weak acid or weak base titrations require an indicator with a more carefully selected transition range. Lecture 28. Acidic and basic buffers. A buffer resists large changes in pH when a small amount of acid or base is added. An acidic buffer contains a weak acid and its conjugate base. Acetic acid and acetate are a common example. A basic buffer contains a weak base and its conjugate acid. Ammonia and ammonium are an example of this type. Both components are necessary. One component removes added hydronium ions, while the other removes added hydroxide ions. A buffer cannot keep the pH perfectly constant, but it makes the change much smaller than it would be in an unbuffered solution. Lecture 29. How a buffer responds. Consider a buffer containing acidic acid and acetate. If a small amount of strong acid is added, acetate reacts with the added hydrogen ions and forms acidic acid. If a small amount of strong base is added, acidic acid reacts with the hydroxide ions. This produces acetate and water. In both situations, the strong acid or strong base is converted into a weaker substance. The amounts of acidic acid and acetate change slightly, but both components remain present. Because their ratio changes only a small amount, the pH also changes only slightly. Lecture 30. The Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation connects the pH of a buffer with the acid strength and the ratio of its components. The pH equals pKa plus the logarithm of the conjugate base concentration divided by the weak acid concentration. If the two concentrations are equal, their ratio is 1. The logarithm becomes 0, so the pH equals pKa. Increasing the amount of conjugate base raises the pH. Increasing the amount of weak acid lowers the pH. If strong acid or base is added, complete the stoichiometric reaction before using this equation. Lecture 31. Buffer range and capacity. A buffer works most effectively within approximately 1 pH unit of its pKa. In this range, the ratio of conjugate base to weak acid is between 1/10 and 10. Buffer capacity describes how much acid or base can be added before the pH changes significantly. A buffer with higher concentrations of both components has greater capacity. Two buffers can have the same pH if their component ratios are equal. However, the more concentrated buffer can neutralize more added acid or base. Buffer pH depends mainly on the ratio, while buffer capacity depends on the total amount present. Lecture 32, pH and solubility. pH can affect the solubility of ionic compounds containing acidic or basic ions. Consider solid iron 3 hydroxide in equilibrium with iron 3 ions and hydroxide ions. When acid is added, hydrogen ions react with hydroxide ions to form water. Removing hydroxide causes the equilibrium to shift toward dissolving more solid. The solubility therefore increases. When base is added, the hydroxide concentration increases. The equilibrium shifts toward forming more solid, so solubility decreases. This is